So this is number 3 on October 2021, isn't it? Type. Okay, let's read the first question, please. Okay, here they said that a student carried out experiments to determine the enthalpy change for the hydration of anhydrous copper 2 sulfate to form hydrated copper 2 sulfate. To find the enthalpy change of the solution anhydrous copper 2 sulfate, 25 centimeter cube. Hello, Yamavi. I allowed you recording. To find the enthalpy change of
I'm
solution.
very sorry, I lost track of time.
Okay, Mavi, it's okay. To find the enthalpy change of the solution of anhydrous copper 2 sulfate, 25 centimeter cube of distilled water was placed in a polystyrene cup and the temperature measured at 1 minute intervals. After 2.5 minutes, 7.5 grams of the anhydrous copper 2 sulfate was added and the mixture stirred continuously, and they have given us the results. Now plot a graph. Abdurrahman, what are we going to draw on the y-axis and what are we going to draw on the x-axis?
On the y-axis is the temperature.
Yes, excellent. We have to draw here the temperature. And here is the time. Type, okay. We have to number here 1, 2, 3, 4, 5, 6, 7, 8. So this could be 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And here we have starting from, we can say 20, 21, 22, 23, 24, 25. No. So here 22, 24, 26, 28, 30, 32, 34, 36. So this could be. So here we can say 22, or we can say 20, 22, 24, 26, 28, 30, and then 34, 32, 34, 36, 38. Right. Okay, so 1, 0 against 21.1, so it's here. And then we have 1 against 21 and 2 against 21. And then 22.5, there's here we are going to add the 7.5 grams of the copper sulfate. At 3 we have 30, at 3 we have 34.2. At 4 we have 37.6. Then we have 36.9. This is 36.9. And then we have 36.1. We have 35.2. We have 34.3. Okay. Now they said determine the maximum temperature change using your graph. You must show you're working on the graph. Alishba, what are we going to do to find the temperature change?
You draw a line through the first 3 points.
The first 3 points, okay.
Should I draw it on the graph?
Okay, I need to draw it. If you can, then it's okay. Can you do it? Can you annotate?
Okay. I'll just tell you, Miss.
Type, okay.
The next points you draw a line of best fit through of them.
Yes. Is this point should be included or not? This
No,
point?
it's an
No.
anomalous point.
Yes, it's an anomalous point, so we have to draw a line of best fit. So Yani, I'm not sure this is a good line or not. I'm going to remove it. Okay, and then what are we going to do next? Yes.
From 2.5, you
Yes.
draw a line upwards.
Yes, excellent. From 2.5, we are going to draw a line upward until it meets with the until it meets here. Yes, and then
You go across.
And go across. Yes, and see where is the type. So what is the initial temperature, ya Alishba?
22.5.
No, the initial
Oh, sorry,
one.
22.1.
It's 21 only. This is 21, isn't it?
Okay.
So it's 21. And what is the final temperature?
That's 34.3.
Where are you? Where is the where is this
I was
34?
reading from the table that you wrote.
No, we don't read from the table. We read here from the graph, isn't it? We read from the graph.
Okay.
Where is the maximum temperature?
38.2.
This is 36, this is 38, this is 38, and this is 40, isn't it? So this will be 38 point, I think 5.
38.2 or 5. Okay.
No, it's not 2, because every single line here means 0.2, 0.2, yes. Because this is 37, this is 38, this is 40. Okay, so this is 39 in the middle. So here you have 38.2, 0.4, 0.5. Or you can say 38.4, isn't it? It's 38
Okay.
point.
I just couldn't see the lines properly. That's why.
Type, okay. So this is 38.4. And when we subtract 21, we get 17.4, isn't it? It should be 17. Yes. 17.4, the delta T equals 17.4 degrees Celsius, isn't it? Type, okay. Okay, Mavi, the value of the enthalpy change of this experiment was minus, let me remove this. So the value of the enthalpy change from this experiment was minus 39 kilojoules per mole. Give one possible reason why this value is different from a data book value of minus 61.4 kilojoules per mole.
So the value we obtained from the experiment was less exothermic than that of the data booklet. So that means that there was heat loss to the surrounding.
Yes, excellent. Excellent, Timab. since the enthalpy change here that was got experimentally was lower than that present in the data booklet, then this means that there were heat loss during the experiment. Yes. Okay. We can also say that as we usually say, that the density of the solution is more than 1 gram, but we consider it to be 1 gram per centimeter cube. We usually consider the density of the solution to be 1 gram per centimeter cube, but of course, this is an approximation. Okay, so the best answer that we can say that there is heat loss during the experiment. تمام, excellent. Miral, after another experiment to find the enthalpy change of the solution of hydrated copper 2 sulfate crystals, the student constructed the Hess cycle shown. Calculate the enthalpy change of hydration for the conversion of anhydrous copper 2 sulfate to hydrated copper 2 sulfate.
So you do the minus 39 and then minus the 5.6 because you're
Yes.
switching the direction.
Yes,
So
excellent.
it's minus 44.
Minus 44.6 kilojoules per mole. Yes, excellent. Excellent, Miral. Do you have any question?
No, doctor, thank you.
Okay, you're welcome. Okay, double I, Rodina. Give one possible reason why the enthalpy change of hydration in DI could not be found directly by experiment.
One second, miss.
Yes, excellent. Yes, it might be excellent. Yes. What we usually say here, because we have both reactants. Yes, excellent, Alishba. Because both reactants and products are in the form of solids. So whenever we have solids, we usually say that it is hard to measure the temperature change of a solid. Okay, it is difficult, or it is it is difficult to measure the change in temperature of a solid. So here we have two solids, so it's difficult to measure the temperature change within solids. Okay, this is what we usually say whenever we have solids. Mavi said, difficult to know the exact amount of energy supplied when exactly 5 water moles is added. Yes. Yes,
Miss,
it is
can
hard.
you say-
Yes. Yes, yeah, Rodina, تفضل.
Say that it's hard to add the correct amount of water.
Yes, of course. It could be hard to add the correct amount of water. Yes. Excellent. You can say so. طبعا. Yes, you can say so. Yes, might be excellent. Okay, Abdurrahman. Number 4. Students were set a challenge by their teacher to produce a chemical clock measuring a 20-second time interval. They used an opaque solution that became transparent, allowing a black cross to become visible after 20 seconds. This is the white paper with the large black X. The students investigated the effect of temperature on the results and plotted a graph. As the temperature increases, the time decreases. In this type of experiment, 1/T, where T is the time, may be used as a measure of the rate of the reaction. Calculate the rate at 15 degrees Celsius to a suitable number of significant figures. Include units in your answer, Ya Abdurrahman.
Okay, so at time 15, so at temperature 15, the time
Yes.
was 33.
Okay, so from 15 we go upward, isn't it? Until we meet the curve and see the temperature, isn't it, Ya Abdurrahman? Wala, what did you do?
Yes.
Yes, okay. So the time here is 33. Okay, and then they want the rate.
So the rate will be 1 over 33.
Yes, as they said that the rate is equal to 1 over time, so 1 over 33. And what did you get?
0.0303
0.303.
per second.
I think there is a zero here.
Yes, 0.03.
Okay. So the rate has the... Yes, okay. So this is the rate type. Sketch a line showing how the rate of the reaction varies with temperature for this reaction. Alishba, sketch a line. Okay, 1 minute. Just because here there are 3 marks. Include units. We didn't include units.
I said per second.
You said per second. So you second minus 1. Type, okay. Yes, excellent. Type, Alishba. They say sketch a line showing how the rate of the reaction varies with temperature for this reaction. Rate against temperature. Here we were drawing time against temperature. And they said that the rate is equal to 1 over time. So can you sketch the rate against temperature here? Okay, now you draw a straight line, but here there was a curve, isn't it, Alishba? When we draw the time against temperature, there was a curve. And so if you take 1 over time against the temperature, it will also show a curve, isn't it?
Oh, okay. Yes, miss.
So we can draw it in this way because it's the opposite of the time. So we can draw it in this way, starting also from the origin, we can draw it in this way. Okay.
Wait, miss, why would it, but I don't understand. Why would it be a curve?
Because here in the, we said that the rate is equal to 1 over the t, 1 over time. So if the time is with the temperature, we have a curve. So if you draw 1 over the time, which is the rate against the temperature, it will give you a curve, but in the opposite direction. Isn't it? Understand?
Oh,
Because
okay,
the rate
yes.
is equal to 1 over time. It's the opposite. Amen. Type. Okay, Mavi, evaluate the students' results and decide whether it is necessary to repeat their experiments. I'm going to show you what they did before. Evaluate the students' results and decide whether it is necessary to repeat their experiments.
Do we say that they do have to repeat the experiment since they got like an anomalous change at 40 degrees?
What, would you please repeat what you said? Are they going to
do we
repeat
say
yes.
Do we say that they have to repeat the experiment because there was an anomalous point at temperature 40 degrees?
Okay, but yeah, you can say so. But of course, this is only one anomaly. Yani, beside all these, we have 1, 2, 3, 4, 5 points that were okay, but only one anomaly. So they don't have to repeat the experiment because it was only one anomaly and it was excluded away when we draw the curve. So yani, it's not necessary to repeat the experiment. Okay.
And so what
Because,
exactly are we supposed to evaluate?
excuse me?
So what exactly do we have to evaluate? I don't get it.
You have to say that there is only one anomaly. This is the evaluation that you do. You say that there is only one anomaly getting out from the curve, and this means that it is not necessary for the students to repeat the experiment, only to exclude it from the graph, as they did here.
Oh, okay. Yeah, I get it now.
Okay. Thank you so much, Miral. State how you would change the conditions to make this chemical clock measure 40 seconds at 22 degrees Celsius. You have to read the question once more, and then I'm going to scroll up.
Doctor, could you scroll up, please?
Yes. We wanted to measure 40 seconds at 22 degrees Celsius. So this is the 22 degrees Celsius. It should here go to about 20, yani, about 19 or something like that, about yani, more or less 19 or 20. So how can we let it be at 40, to measure it at 40 seconds?
So does it want the rate of the reaction to decrease?
Yes, excellent. So what
do
are
we-
they going to do?
Uh,
Yes.
We can reduce the concentration of the reactants.
Yes, excellent. Yes, excellent, Yamiral. We have to reduce the concentrations of the reactants so as to decrease the rate, and so the time will be greater, because they want at what did we say, at 22 degrees Celsius. At 22 degrees Celsius, we want the time to be at 40, not to be at about 20. So we have to increase the concentrations. When we increase the concentration of the reactants, this means that it will take more time for the reactants to react together. Sorry, to reduce, I'm sorry, to reduce the concentration. And when we reduce the concentration, it will take more time for the rate of the reaction to take place. Yes, excellent. We have to reduce the concentration of the reactants, or to decrease them, yeah. Okay. Yes, excellent, Yamiral. Do you have any question? Any one of you, do you have any question? Type, let's see here, number 5, Rodina. A technician found a bottle of sodium hydroxide solution at the back of a cupboard. The technician determined its concentration by titrating 25 centimeter cube samples against 0.5 mole per decimeter cube hydrochloric acid from a burette. The results are shown. Complete the titer tables. Sorry.
Okay, so for the first one, it's 22.6 because I minus the final reading by the initial reading.
Yes, excellent. 22.6. This is the rough one.
Yeah, the next one is 21.25.
Yes.
It's the same. And then it's 21.6. And then 21.3.
Yes, excellent. State why the value from titration 2 was not used to calculate the mean.
Because it was not concordant.
Yes, excellent. It is not concordant with the others. Yes, excellent. So we exclude it. Calculate the concentration of sodium hydroxide solution in mole per decimeter cube. Rodina 2.
1 second, miss. So first you work out the moles of the hydrochloric acid because they gave you the volume
Yes.
and the
Yes, excellent. So which volumes are we going to use here, Rodina? We excluded this.
25.
Huh.
We use the mean, so you add up the concordant titers and divide them by 3. So
Yes.
concordant titer 1 and 4.
So the volume of hydrochloric acid will be 21.25 plus 21.3, isn't it? Plus 21.35 divided by 3, which means 21.3
Yes.
centimeter cube. Okay, and then
And then you divide that by 1,000 to get it in decimeter cubed,
Yes, excellent. And find what?
and then multiply it by the concentration, which is 0.5, to find the moles of hydrochloric acid.
Yes, so 21.3 divided by 1,000 times 0.5. What did you get?
I got 0.01065.
Okay. And then they want the
That's the
concentration of
moles,
sodium
so
hydroxide.
we have the moles, and the ratio is 1:1, I think, because
Yes,
they haven't
excellent.
given any information.
Yes, it's 1 to 1.
So if the
But you
ratio is
can, if they even don't get you in any information, you have to write the equation by yourself. And it's HCl plus sodium hydroxide gives sodium chloride and water, which means that it's 1 to 1. But sometimes they are going to give you any other acid, for example, sulfuric acid. Then you have to write the equation first to determine the mole ratio. Okay, and you don't depend on them. Sometimes they don't give you the equations. So yes, so
Okay.
the mole ratio is 1 to 1. So
you rearrange the equation to find concentration, which equals moles over volume. And we
yes,
said that the volume of sodium hydroxide that's titrated is 25 centimeter cubed.
yes,
So you divide it by 25 centimeter cubed. You divide the 25 by 1,000, and then you
yes. So what do you get here for the concentration?
0.426.
0.46 mole per decimeter
426.
cube. Yes, excellent. Thank you so much, Herodina. Do you have any question, any one of you? Okay. Abdurrahman, each reading of the burette has an uncertainty of plus minus 0.05 centimeter cube. Calculate the percentage uncertainty in titration 4. Titration 4 is 21.35.
So it will be 0.05
Yes,
multiply 2
yes, excellent.
over 21.35
Yes,
multiply 100.
yes, excellent. Did you get an answer?
Will be 0.47% plus minus, of course.
0.47%. Type, okay. Abdurrahman, state the color change that would be seen at the end point in this titration using phenolphthalein as indicator. Do you remember
Pink,
what did they
colorless.
start with? Yes, from pink to colorless. Excellent, because we started with sodium hydroxide, so it will be pink and change to colorless. Yes, excellent. Okay, I think we finished this paper. I mean, do you have any question here? Type. Let's see, Jan, 2022. Type. Okay, this is Jan, 2022. This question is about ammonium chloride, a soluble ionic compound. An aqueous solution of ammonium chloride contains both ammonium ions and chloride ions. State what would be seen on the addition of acidified silver nitrate solution to an aqueous solution of ammonium chloride. Alishba?
It would be a white precipitate.
Yes, excellent. A white precipitate. Of course, I prefer that you write precipitate يعني in a complete word, not PPT. Describe a test, Alishba, to confirm that the ammonium ions in the solution of ammonium. Describe a test to confirm the presence of the ammonium ions in a solution of ammonium chloride. Include the result of the positive test. Yes, Alishba, what is the test for ammonium ions?
Um, 1 second, miss.
Okay. You remember that we used to add, this is the ammonium salt, any ammonium salt. We place the sodium hydroxide. We place sodium hydroxide here and we warm. And then there will be a gas coming out. This gas is ammonia. So we test for it by, yes, excellent, Rodina, by approaching a damp red litmus paper, it will turn blue, or else we can approach a glass rod wet with HCl, it will form white smoke, white clouds. Okay, so this is the test for the ammonium ion. We say place the salt in a test tube and add sodium hydroxide solution and warm, and then test the vapors using a damp red litmus paper. It turns blue. This means that we have ammonia. Or we get a white smoke with a glass rod wet with HCl. Okay? Okay, Alishba?
Okay, miss, thank you.
Hi, you're welcome. Now, let's go to the next question. Mavi, you can read this. Okay, did you finish this?
Yes, doctor.
Okay. So now they got this curve. Give 2 reasons why the student stirred the solution in steps 3 and 4.
Is it the first, like for the first reason is to dissolve the salt, the
Yes.
ammonium chloride salt.
Yes, excellent. For the
And
in step 4,
Is the
they stirred to dissolve the
Yeah.
ammonium chloride. Yes, and in the 4th step,
is it to measure the is it to evenly distribute the heat or temperature?
yes, excellent. To evenly distribute the temperature. Yes, excellent. We stir so that we can get a uniform temperature. Yes, excellent, Mavi. Type. Okay, Mavi 2. Use the graph to determine the maximum temperature change delta T in this experiment. You must show you're working on the graph.
Okay, so since here they started immediately, like from 0 measuring the temperature, they didn't initially measure the temperature before.
Yes.
There's going to be a straight line from the first point going down to the point before they added the and also from down there. I mean up
We
there.
have to extend it to here, isn't it?
Yeah, and the other one too.
Which one?
The one starting from the 19 point something.
Yes, you mean this line? You mean, shall I go to the 0 كده? You mean this? Or what?
No, doesn't it have to go through the other points too, right?
No, it shouldn't go to the other points. If you remember, before, when they give you, for example, a reaction at which there is an exothermic reaction, they give you the initial temperature, they place, for example, a certain volume of water in a beaker, and they measure the temperature at 3 different times. For example, after 1 minute, or after 1 second, 2 seconds, or 1 minute, 2 minutes, 3 minutes. And so we get this initial temperature, isn't it?
Yes.
And then they place, and then at this time, they place the solid. That is after, for example, 2.5 minutes, after 3 minutes, they start to add the solid. So when they add the solid, you get here a certain anomalous point, and then, for example, another one, and then the temperature starts to cool, isn't it? And so when you want to find out the difference in temperature, you draw the line of best fit like this, and then starting from the time at which they added the solid, you go upward until you meet the straight line, and this will be the final temperature, and the difference in temperature will be this one. This is the delta T between the initial readings and this line. But in this experiment, they didn't do so. They did the opposite. They placed the solid first in the beaker. They placed the solid in the beaker, and then after they measured the temperature of water, they added to the solid. Understand? So they added the solid first and then the water. So there was no time to measure more than one temperature for water. They just measured its temperature and poured it over the solid, where the solid dissolved at once. So this will be the initial temperature. You see in the experiment?
Oh, yes, that's 0.
Yes. They said fill a 50 centimeter cube measuring cylinder with deionized water and measure the temperature of the water using a thermometer only once. And then they poured it over the solid. Okay?
Yeah.
So they didn't do this part. They didn't do this part. Otherwise, your curve will be like that. It would have been like this. And then when they add the solid, and then you get this line. Because this is an endothermic reaction. As you see, the temperature dropped. But this is an exothermic reaction where the temperature increased. Okay, all? Can you see the difference? This is an exothermic reaction. They start from a low temperature, and then when the solid is added, the temperature rises, and then after the solid dissolves, it starts to cool. The solution starts to cool. But here, we started with a high temperature, with respect to the others. We start with a high temperature, and then when the solid is added, the temperature dropped. It dropped, and then when it gains heat from the surroundings, it starts to rise. So it's the opposite to this curve. Okay, can you see the difference? So here, the temperature, after it dropped when the solid is added. It's just like when they put here an anomalous point. So these are anomalous. And then we draw the line of best fit, and we extend it to the y-axis and find this is the initial temperature, T1, and this is the final temperature, T2. And when we subtract them from each other, we get the difference in temperature. Okay, Mavi? Of course, I'm talking to all of you, not only to Mavi.
Yes, clear. Thank you.
You're welcome. So here we have to find, yes, Yamira.
Why is the final temperature at the 0 seconds? I don't understand why it's not.
No, this is the initial, not the final.
The final, sorry. I don't understand why the T2 is at 0 seconds.
No, we don't get it at 0 seconds. We just extend the line until the 0, yes, until the 0, until the 0 seconds, because they started to add the water to the solid at this point. Okay, they started to add the solid here. Yani here, when they started to add the solid, for example, it was at 2.5 minutes or at 3 minutes, isn't it? That's why we extend our line until it meets with the time at which the solid is added. But here the solid was added from the beginning. From the 0 time it was placed. Understand, Yamiral?
Yes, doctor, thank you.
You're welcome. So here, when we subtract T1 minus T2, we get the delta T. T1 minus T2, we get the delta T. So we have 19.8 minus 10.6.
Is it 19.8 or 19.7?
19.7. Okay, so 19.7 minus 10.6, and you get
9.1.
9.1 degrees Celsius. Okay, So this is an endothermic reaction, not an exothermic one. That's why the full curve is the opposite. And the second information that we get from here is that since they didn't place the water first and then add the solid after 2 or 3 or 2.5 minutes or whatever, since they added the solid after a certain time of minutes, that's why we have to start from the point or the time at which they added the solid and go upward until we meet the straight line. But here they placed the solid and they added the water, which means that as if the solid is added from the 0 time, not after 1 minute or after 2.5 minutes or after 3 minutes. The water was added to the solid from the 0 time. So that's why we have to go from this point until we meet the line at 0 time, because it's the time at which the solid is placed. Do you understand all? Do you have any question? Okay. Mirar? Another student carried out the experiment using a polystyrene cup in place of the glass beaker. Explain how this student's graph would be different, and you may annotate the graph as part of your answer.
The polystyrene cup reduces the heat loss to surroundings, so delta H would be bigger.
Yes, but they want you to show them what happened here on the graph.
I'm not sure, miss.
Okay. So if polystyrene cup is used, this means that the temperature will not be lost, like in case of the glass beaker, isn't it? Which means that here the minimum temperature that we got here should be lower. The minimum temperature that we got here should be lower. Why? Because we said that here the temperature drops, but it will not return back to the original temperature around us, because the temperature was not lost through the glass beaker. We now use a polystyrene cup, isn't it? And then here the temperature started to be regained in a certain rate, but now the polystyrene cup cannot return back the temperature as the surroundings as quickly as here. It will be slower. Okay. So this means that here we are going to use, here the temperature drop will be lower, and then the minimum will be will be lower here, and then we are going to lose we are going to gain, I mean, the temperature of the surrounding, but at a slower rate. And this means that the line here will be the rate is slower. This means what? The time will be greater, and the temperature gain, I mean, it will be like this. So the temperature is going to be gained more slowly. 1 minute, best to make sure that what I did is correct. It will need more time for this temperature to be gained. So needs more time for this temperature. Yes. So this temperature will be gained more slowly.
Doctor, why is it gained
Yes.
more slowly? I don't understand.
Because you are using a polystyrene cup, isn't it? So the polystyrene cup is taking its heat as it is. It doesn't take heat from the surrounding in the same rate as if you are using a glass beaker. Now the temperature dropped and it's going to rise, isn't it? But the rise will be at a slower rate. It will be at a slower rate. Why? Because the polystyrene cup will not allow the heat from outside the cup to enter to the solution. Okay, as the polystyrene cup does not allow the heat to go outside, it also does not allow the heat from outside to go inside. Understand me? So it will regain the temperature of the surroundings, but at a slower rate. Okay.
Okay, doctor, thank you.
You're welcome. Yes, Yamavi.
Doctor, but isn't it when in like an endothermic reactions, like heat energy is taken in from the surrounding?
Yes.
So how will it take in the heat energy from the surrounding?
It will take it, but at a slower rate than if you use a glass beaker. It will take it from the surrounding, but at a slower rate.
Does that mean that the temperature decrease will be greater?
No, it will return back to the original temperature of the room temperature, but at a slower rate. It will take time.
No, I'm talking about the initial decrease in temperature from the 19.7.
You mean here?
Yeah.
It will be slower. It will be lower. Why? Because because it will not lose this heat outside to the surrounding quickly. Okay, and here you reach this temperature and then it started to gain the heat energy from the surrounding, starting from here. But if you are using a polystyrene cup, it will lose more heat because it's not going to give the heat energy directly to the surroundings, but it will keep it for itself for a time and then start to rise. Understand what I mean?
But then doesn't that mean it keeping its temperature or heat to itself? Doesn't that mean that the temperature should be higher since it's not released easily?
Yes, but when it loses the temperature, it will take some time to lose it. So at the polystyrene cup itself, the temperature will be lowered more, and then it will start to lose it to the surrounding. Okay, understand what I mean? It's going to be inside. It is still lowering. It is still being lowered, but it will not start to rise except after some time. It will take time to start to rise, not like here. Here it will start to rise because it will take heat from the surrounding, and so it will start from here to rise. But if the polystyrene cup is keeping the temperature for itself, then it will not start to gain until after some time. And so that's why the temperature decreased more and then it started to rise.
Oh, yeah, I get it now. Thank you.
Okay, you're welcome. Type, okay. Rodina, the experimental results of another student were used in the equation shown to calculate the enthalpy change delta H for the dissolving 1 mole of ammonium chloride in excess water. The delta H is plus 14,500 joules per mole. In the equation, the M is the mass of the solution 50, the specific heat capacity 4.18, and delta T is the maximum temperature change of the solution, N is the moles of ammonium chloride. State 2 assumptions made in this calculation. You do not need to justify your answer.
The first assumption is that the specific heat capacity of water is equal to the specific heat capacity of the solution.
Yes, excellent. What else?
And the second, I think the density,
Yes.
you're assuming the density is 1
Yes,
gram per.
Yes, Rodina, excellent. because your voice is lagging a little bit. But as you said, this was excellent. You said that we assumed that the density of the solution is equal to 1 gram per centimeter cube, although of course it's different than that because it's a solution and not that of water. They said you do not have to justify, but I'm just justifying if they at any time they would ask you. So here the specific heat capacity of water is they assume that it is 4.18, although the heat capacity of the solution would differ than that because the heat capacity of the solution is not like that of water. We have a solution, we don't have water, but the specific heat capacity of water is 4.18 and we are using it here. Although for the solution it would differ. And also the density, we assume here that the density of water is equal to 1 gram per decimeter cube, although the density of the solution is not 1 gram per decimeter cube. How are we assuming the density? You assume that the density of water is equal to 1. That's why you say that the mass of the solution is 50 grams, and these were the 50 centimeter cube of water that you placed here in the experiment. And we assume that the volume is equal to the mass. We assumed here like that because we know that the density equal mass over volume. So we assume that the density is equal to 1. And so we replaced the volume that we took of water, we replace it by the mass here. Okay, Alishba? And the third thing, of course, they only want 2 assumptions, but the third assumption that we did not consider the mass of the ammonium chloride in our calculations. We didn't take it into our consideration. Okay. Yes, excellent. Yes, Yamal.
Can we also say that the specific heat capacity of the beaker has no effect? This is another assumption.
The specific heat capacity of what?
The container or the beaker has no effect.
Yes, you can say so, but we usually say so whenever we are using something called the bomb calorimeter. Are you talking about the bomb calorimeter or what?
No, I'm not sure about the name, but I've seen that once in a mark scheme, like in paper in
Yes.
Unit 2.
Yes, yes. We assume it, yes, whenever we are using what we call a bomb calorimeter, yes. But let it be the last thing to say, Let the assumptions that we can say about the density, about the specific heat capacity, and about ignoring the mass of the ammonium chloride.
Okay, thank you.
Okay, you're welcome. Type, okay, Abdurrahman, the total percentage uncertainty in this experiment was 2.6%. Show that the enthalpy change of 14.5 kilojoules per mole is consistent with a data book value of 14.8 kilojoules per mole.
So firstly, we multiply 2.6% by 14.5.
2.6 over 100, you mean?
Yes.
By 14.5.
The answer is 0.377.
Okay, kilojoules per mole. Okay. And then?
So we add this to the 14.5.
We add the 14.5, yes. We add it to what?
To the 0.377.
Plus 0.377.
The
So,
0.377.
Uh,
So the answer is 14.877.
no, you add the 0.377, isn't it?
Yes.
So what do you get?
14.877.
14.877. Yes, okay, which is, they say that it is consistent with the data booklet, isn't it?
Yes.
So since we got this value, this means that it is very near to the 14.8 kilojoules per mole, which means that it is consistent with the data booklet value.
Yes.
تمام. Yes, excellent. Do you have any question here on what Abdurrahman did?
Miss, I don't understand this question. Can you go through it
Okay.
again, please?
They said that in the experimental method, we got 14.5 kilojoules per mole, isn't it? Yani they say so. And in the data booklet, the value was 14.8 kilojoules. Yani there was a 0.3 decimal points that are missing. Yani. So they say that if the total percentage uncertainty in this experiment was 2.6%, show that this value that we got experimentally is consistent with what is present in the data booklet, 14.8. So the percentage uncertainty means that you add 2.6% to the 14.5 because this was a percentage uncertainty. We say plus or minus, isn't it? We say plus or minus 2.6%. So if you calculate the 2.6% of the 14.5, this means that we got 0.377. Of course, the percentage uncertainty means plus or minus. So if we take the plus, this means that we will get 14.877, which means that it is consistent with the value that is present in the data booklet. And if you add the percentage uncertainty that is present in this experiment, you will get a value that is very near to the data booklet's value. Understand what I mean, or would you like me to explain it once more?
Yeah, Miss, I understand it, but the first part I'm confused. Why did we multiply by 14.5?
Because this is what you get experimentally. This is what is found in the data booklet. And the percentage uncertainty is on the experimental part, not on what is found in the data booklet. Okay.
Okay, Miss, thank you.
The uncertainty is in the experimental work, not in the theoretical that is present in the data booklet. So you say that if there is an uncertainty of 2.6, what should this 2.6 represent from the value that we got? It represents 0.377 kilojoules per mole, which means that this value is either added to the 14.5 or removed from the 14.5 because we say plus minus, isn't it? We say plus minus, isn't it? So if you add it, of course, if you subtract it, you will get a value that is 14.5 minus 0.377. So what do you get? You get here 14.1. And if you add it, you get 14.877, which means that this value is in between, the value in the data booklet is in between the values that we got experimentally. It's in the range, the 14.8 of the data booklet is in between the range of 14.1 to 14.877 of the 2.6% uncertainty. Understand what I mean, ya Rudaina?
Yes,
Yani
Miss.
when we say uncertainty, it means plus or minus the value that we got. When you say 14.5, this is an absolute value. But we have uncertainty. We say plus minus a certain value. The plus minus this value, we got it from the percentage uncertainty that they gave us to find out how much am I going to add or subtract from the value I got experimentally depends on the percentage uncertainty they gave us. So it's plus minus 0.377, which means that if you add it to the 14.5, you get 14.877. Even if you subtract it from the 14.5, you get 14.1. And the value 14.8 lies between the 14.1 and the 14.877, which means that our values, experimental values, is consistent with that found in the data booklet. Okay?
Okay, Miss, thank you.
You're welcome. Type, okay. Would you please all read the question 2? Okay, Alishba, state the measurements that should be made.
The amount of precipitate formed.
No, we don't have a precipitate here. Here you have an organic compound that has this mass, 1.33 grams of the organic compound X, okay? And you passed oxygen to burn it or to combust it. It forms what? Whenever you have an organic compound that contains carbon, hydrogen, and oxygen, and you burn it, what do you get?
H2O and CO2.
Yes, H2O and CO2, isn't it? So when they burned this organic compound using oxygen, they got water and they got carbon dioxide. So they trapped the water through a U-tube containing silica gel. The silica gel will absorb the water. And then what will be left is the carbon dioxide. They pass it through another U-tube containing soda lime that absorbs the carbon dioxide, and the excess of oxygen will pass and go outside the apparatus, okay? So state the measurements that should be made. They want the mass of hydrogen, of carbon, the mass of hydrogen and of carbon present in the 1.33 grams of X were determined by passing its combustion products through the apparatus shown. So we want the mass of hydrogens and carbons that are present in the water and carbon dioxide. So what are the measurements that should be made during the experiment to get the masses of hydrogen and of carbon?
The amount of H2O absorbed and the amount of CO2 absorbed.
Yes, and how can you get them? How can you get them? Yani how can you get the mass of water absorbed and the mass of carbon dioxide absorbed? What you say is correct, but how? Do you want you to show them that you understand? How can we get them?
I'm not sure, miss.
Why? You had a tube containing silica gel, and what happened after the water passed through it?
Okay. Would you measure the mass before and after
Yes, that's
after it
all
was
you have
heated?
to do. Yes, excellent. You have to measure the mass of the U-tubes, both U-tubes, before and after the combustion of the organic compound, isn't it? So before you have the U-tube containing the silica gel. So you measured its mass. And then after water was trapped in it, you measure the mass once more. From the difference in mass, you can get the mass of water, isn't it? And for the other, it's the same. You have a U-tube containing soda lime. So you measure the mass of the U-tube containing soda lime before combustion and after combustion when it absorbed the carbon dioxide. So you can, by the difference, you can get the mass of carbon dioxide, isn't it? Okay. Give two reasons, Mavi, why pure oxygen and not air should be used. Didn't we solve this paper before? I remember this question.
Yeah.
Okay. Give two reasons why pure oxygen and not air should be used.
Is it so that there would be no nitrogen that would react?
Okay, but nitrogen, will nitrogen react with the organic compound that contains carbon, hydrogen, and oxygen? Or what will react? What is going to react? It's not nitrogen.
Is it the water vapor?
Yes, excellent. The water vapor. The water vapor will form what? It can collect here as water, isn't it?
Yeah.
If we use air instead of pure oxygen, if we use air instead of pure oxygen, it contains water vapor. And the water vapor will be collected here in the silica gel together with the water that we get as a combustion product from the organic compound, isn't it? And what else? What else
Is it
can
the
be
carbon
collected?
dioxide too?
Yes, excellent. The air also contains carbon dioxide. And so the carbon dioxide will pass and collect here together with the carbon dioxide that is formed during the combustion of the organic liquid, isn't it? So that's why we have to use pure oxygen and not air, so as to exclude the moisture, sorry, the water vapor or the water vapor that is present in the air, and the carbon dioxide that could also be present, not it is already present in the air, to collect together with the combustion products, the water and the carbon dioxide from the organic liquid. Yes. Do you have any question here? Yes, excellent, Mavi. Miral, the experiment showed that 1.33 grams of X contains 0.14 grams of hydrogen and 0.63 grams of carbon. Calculate the empirical formula of X.
Okay, so first you write the mass of each element. So under the carbon you write 0.63, and under the hydrogen you write 0.14. And then you write the molar mass. So for carbon,
Okay, but we still have an oxygen, isn't it? We still have oxygen in X. At the beginning, they said that X contains carbon, hydrogen, and oxygen.
Yeah, oxygen is 0.56 grams.
The oxygen is 0.56. Did you calculate it, Yani?
Yeah.
Okay, so it's going to be 1.33 minus 0.14 plus 0.63. So what did you get?
0.56 grams.
0.567 grams. Type, okay.
No, just 0.56.
Type, okay. And then?
You write the molar masses. So for carbon, it would be 12. For hydrogen, it would be 1. And for oxygen, it would be 16.
Yes.
Then you calculate the moles for each. So for carbon, it's 0.0525.
Okay.
For hydrogen, it's just 0.14. And then for oxygen, it's 0.56 over 0.035.
0.035 type, okay.
And then you divide by the smallest value, which is the
Yes.
oxygen. So to find the ratio. So for carbon, it would be 1.5. And for hydrogen, it would be 4.
Okay.
And then your whole number, so you multiply everything by 2. So carbon would be,
Excellent.
hydrogen would be 8, oxygen would be 2.
Excellent. So the empirical formula is C3H8O2, isn't it? Yes, excellent. Excellent, Miral. Rhodina, when phosphorus 5 chloride is added to X, steamy fumes are seen. State what can be concluded about compound X from this observation only.
It contains an OH functional group, so it's an alcohol.
Yes, it's an alcohol. Excellent. We conclude that it's an alcohol. Or it contains an OH group, as Rodina said. Compound X is converted via rhodina into compound Y when refluxed with excess sodium dichromate 6 in sulfuric acid. Compound Y is a liquid that is soluble in the reaction mixture. Draw a label diagram of the apparatus that could be used to separate Y from the reaction mixture.
One second, miss.
Yes.
So we'll use distillation.
Yes,
Because
we are going to use distillation, yes.
So first you draw a pear-shaped flask at the bottom.
We draw what?
Pear-shaped flask,
Yes, okay,
bottom flask.
yes.
And then you add anti-bumping granules,
Yes, excellent.
and then connected to it should be a thermometer and then a condensing tube on the side.
Yes, a steel head. We connect a steel head, isn't it?
Yes.
The steel head is like this. And then we connect the thermometer.
And you have to make sure the thermometer lines up with the opening of where the condensing tube is.
Yes. And then,
Draw the condensing tube.
yes,
And
excellent.
a I forgot the name for it, like a
Receiving adapter.
yes, the very long tube at the end where the distillate is.
You mean here there is a receiving adapter, isn't it? We place a receiving adapter. And then it is connected to another round bottom flask to collect the whatever we want to collect. Okay.
And then from the bottom of the condensing tube, you should label it as water in, and the other one should be water out.
Yes, excellent. Here we say this is a receiving flask.
Miss, you can't use the long delivery tube that goes into a flask.
What is the delivery tube? What do you mean by the delivery tube? This is we call this a receiving adapter, which
So
has an opening. We should have an opening because if the system is all closed, then it could be cracked, it could be broken because it will build up pressure inside it. We have to show that here we have an opening, so to reduce the pressure inside the system. Isn't it, Rodina? What do you mean? Yani, I don't understand what you want me to draw.
No, Miss, that's what I meant. Thank you.
You're welcome. So here we draw a thermometer. Here we write the reaction mixture. The reaction mixture that we want to separate the carboxylic compound Y. Here, of course, we have to show that here is a heat, and these are anti-bumping granules. Okay. Is there anything missing? Of course, this is a steel head, yani.
Yes, I think just label the condenser.
Okay. Anything else? Okay, thank you, Rodina. Abdurrahman, the infrared spectrum of Y is shown. The table shows some infrared absorption data. Okay, we'll return back, but we will see the question. Explain how this spectrum shows that Y contains a carboxylic acid function group, quoting data from the table.
It has a white peak from 3,300 to 2,500.
Yes, excellent. It has a broad peak. It has a broad peak between 3,300 to 2,500 centimeter minus 1, corresponding to the OH carboxylic group. Yes, excellent. And what else?
It also has a C double bond O absorption
Yes.
from 1740 to 1680.
Yes, excellent. It has another peak corresponding to the C double bond O between 1,680 to 1,740 centimeter minus 1. Yes, excellent, Abdurrahman. Does anyone have any question here? Infrared? Type, okay. Alish, but the mass spectrum of Y is shown. Show that the mass spectrum is consistent with Y having the molecular formula C3H4O3. How can we show that from the mass spectrum that the compound has this molecular formula, C3H4O3?
Miss, I'm not sure.
Okay, what do we get, Alishba, from the mass spectrum? Yes, excellent, Yerodine. What do we get? What is the first thing that we get from the mass spectrum, Alishba?
You see the molecular ion peak?
Yes, excellent. The molecular ion peak. Where is the molecular ion peak?
The tallest peak.
No, it's not the tallest peak.
Oh, sorry, the peak at the end.
Yes, it is the peak at the end. This is what we call the molecular ion peak. The molecular ion peak. And what do we get from this molecular ion peak, Alishba?
It's the MR of the compound.
Yes, excellent. We get the molecular mass of the compound, isn't it? The MR of the compound. That's what they want you to say. That if you calculate the molecular mass of the C3H4O3, if you calculate the molar mass of the C3H4O3, what do you get? 12 times 3 plus 4 plus
88.
3. You get 88. And what is this peak? At which, is it 88? Okay.
Yes.
So this is 88. So here we have 90, isn't it? This is 90, which means that yes, the molecular mass of the compound is 88. We get it from the molecular ion peak. The tallest peak is called the base peak. And the base peak, we do not get from it any information. It only shows us that this is the highest percentage of the fragmented parts. Yani the molecule is going to be broken down into simpler ions. And this ion gave the highest percentage. It means that it was, yani, when the molecule was broken, many of the broken fragments are in this form. This is the base peak. Okay, the base peak shows only the base peak that has the highest relative intensity, shows which ion that is being fragmented is found in big amount. That's only what we have to know about the base peak. And of course, they do not ask you anything about it. But from the molecular ion peak, we can get the molecular mass, and it is shown that it is 88, just like when you calculated the molar mass. Okay, Alishba?
Okay, Miss, thank you.
You're welcome. Okay, Mavi suggests the structure of the ion causing the peak at 43 in the mass spectrum of Y. And this is the base peak at 43. So suggest the structure of this ion. We know that it has a C3H4O3, and we know that one of the function groups is a carboxylic group, and the other is what?
Is it 2 carbons and 1 oxygen and 3 hydrogens?
Is it what did you say?
2 carbons and 3 hydrogens and 1 oxygen.
Yes. So what do you expect about its structure? Because they said suggest the structure. You said C2H3O.
Oh, yeah.
Okay, so what do you expect about its structure? Because this is a formula, this is a molecular formula, but they want the structure of the ion. What can it be? What you said is correct, but what do you expect about the structure?
I'm trying to think of a way where we can arrange all the molecules, the atoms together.
Okay.
Can it be like there might be a double bond maybe?
Yes, of course. Yes, excellent. You mean a double bond between the 2 carbon atoms, or where? Where is the double bond?
Between the carbon and the oxygen.
Yes, excellent. So it's a ketone, isn't it?
Yeah.
It's a CH3, C double bond O positive ion. isn't it?
Yeah, and then
Because-
the
because you
other
cannot-
carbon was removed.
You mean the third carbon? Yes,
Yeah,
the
the
molecule
one
is
to the
broken.
right. Yes.
Yes, the molecule is broken, but you got this ion, which gave you the peak at 43. Okay. Yes, Yerodina, excellent. Okay. Miral, compound X contains one type of functional group. Compound Y contains two different functional groups. Use the information in the question to deduce the structures of X and Y. Of course, I can scroll up once more to get the information about X and about Y.
Yes, please, Miss.
Type, okay. So they said that compound X contains one function group. Let's find out what is compound X from the beginning. From the beginning, they said that X has carbon, hydrogen, and oxygen, isn't it? And from the empirical formula of X, what did we get? You were the one that did it. What was the empirical formula here? It was C, I think we multiplied by 2, it was C3.
C3H8O. I forgot.
Me too. Who wrote the empirical formula? Who wrote the empirical formula of X? No one wrote it? Abdurrahman, what was the empirical formula of X?
It was
Yes. Yes, yeah, Abdurrahman. C3H8 what? O what?
C3H8O2.
O2?
Yes.
Type. Okay, so this was the empirical formula in Miral of X. And I think we said that it's an alcohol. When phosphorus 5-chloride is added to X, steamy white fumes are seen, isn't it? So we said that there is an OH group.
Because there's two oxygens, there have to be two OH groups, so it's a diol.
Yes, because they said compound X is converted to compound Y when refluxed with excess sodium dichromate in sulfuric acid, isn't it? And we said that Y contains a carboxylic group. So this means that there are two OH groups in X. Yes or not?
Yes.
Type, okay. So can you give us a structure for X? We have 3 carbon atoms. And what else?
So the first one would just be CH3,
Yes,
and then the second carbon would have one hydroxyl group and then one
Yes.
hydrogen,
excellent.
and the third carbon would have two hydrogens and one hydroxyl group.
Yes, this is the right structure because now we have 8 hydrogens, 3, 4, 5, 6, 7, 8, and 2 oxygens. And then when compound X was heated with potassium or sodium dichromate present in sulfuric acid, compound Y was formed. And we have seen that compound Y contains a carboxylic group, isn't it? From here, we have seen that it contains a carboxylic group. And here we have seen that it also has a CH3, C double bond O positive group. So what will be the structure of Y?
It would be the CH3,
Yes,
C double bond O,
C double bond O.
and then C, I'm
has
not
this
sure,
molecular form.
CH3. And then
C-
the C is to double bond O and then OH.
Yes, it's a carboxylic group here. Because here we have seen that it contains a carboxylic group. And from the molecular ion peak, we have known that it is C3H4O3. So here we have C3H4O3. We have a carboxylic group. And of course, if you have a secondary alcohol in this part, when it is oxidized, it will form the ketone. When it has a primary alcohol in this part, on oxidation, it will give the carboxylic group. So this is Y and this is X. Okay.
Yes,
Any
Dr.
questions here? Yes. Okay. Thank you so much, Emiral. Do you have any question? Any one of you? Any question here? Type. Okay. Let's see number 3. Rodina, would you please all of you read this experiment? Have you finished reading?
Yes, Miss.
Okay. Now, you understood the experiment? Did you all understood what they did here in the experiment?
Yeah.
Okay. Rodina, give the ionic equation for the reaction that occurs when sodium sulfate solution is added to the conical flask in step 2. Include state symbols.
Ba2 plus
Yes, excellent.
plus SO4 2 minus aqueous.
Yes, so both are aqueous since they have ions. So both will be aqueous, gives,
Barium sulfate solid.
excellent, gives barium sulfate solid. So here, when they added the sodium sulfate to the barium chloride, it was to precipitate the barium ions in the form of the barium sulfate solid in order to get rid of the barium ions. Yes, excellent, Rodina. Please, Rodina, give a possible reason why it is necessary to add sodium sulfate solution and justify your answer.
I think it's to remove the barium ions, but I'm not sure.
Yes, excellent, to remove the barium ions. And why do we want to remove the barium ions?
Because then they would form a precipitate with the chromate
Yes.
ion.
Yes, bravo عليكي, excellent. Here we added the barium sulfate. They said give a possible reason why it is necessary to add the sodium sulfate. It is, as Rodina said, to remove the barium ions, because when we add the sodium sulfate, the barium ions would react with the sulfate ions to form barium sulfate. And why do we want to remove the barium ions? Because if they are present in the solution, they could react with the chromate ions and produce barium chromate, which is also a solid like the silver chromate. So we want to precipitate the silver in the form of silver chromate. So if the barium is present, it will also precipitate. It will take part of the chromate ion and form barium chromate. We don't want this to take place. That's why we have to remove the barium ions. So here you are going to say to remove the barium ions so as not to react with the chromate ions, forming barium chromate. Okay. تمام. Excellent يا رودينا. Abdurrahman suggests why the red precipitate of silver chromate only forms after all the chloride ions have reacted.
Because if it was formed before it was because if the precipitate was formed before all the chloride ions have reacted, it would be a white precipitate of silver chloride.
1 minute. They say suggests why the red precipitate of silver chromate only forms after all the chloride ions have reacted. So we say that this is because the what did you say, Abdurrahman? Malish, once more.
Because the precipitate that previously was formed was the precipitate of silver chloride, which was white precipitate.
Yes, and what happens if it is a white precipitate? They say suggests why the red precipitate only forms after the chloride ions have reacted. It doesn't form except when all the chloride ions reacted with the silver ions and formed the silver chloride, of course. And then after all the chloride ions reacted, then the silver will not have except the chromate ion to react with, and so it will react with it, isn't it? So why did the silver chloride precipitate it first? Why did it react with the chloride first? Yani, why did the silver ion did not react with the chromate except when all the chloride ions were removed from the solution? Okay, here we have to say that the silver chromate 6 is more soluble, no, not more reactive, but the silver chromate is more soluble than the silver chloride. That's why the silver chloride precipitated first. It is less soluble than the silver chromate. The silver chromate is more soluble. So even if the silver reacts with the chromate to form the silver chromate, it is more soluble than the silver chloride. So it will not appear in the solution as a precipitate. But when all the chloride ions are reacts with the silver ions, forming the precipitate of silver chloride, then the silver ion will start to react with the chromate ions and form the precipitate, the red precipitate. We say that the red precipitate of silver chromate is more soluble than the silver chloride precipitate. As it is more soluble, it will not appear unless all the chloride in the solution precipitated first, and then the silver chromate starts to precipitate. Or we can say the opposite. We can say that the silver chloride is less soluble than the silver chromate. That's why it precipitated first, because it is less soluble. Shall I write this? We just say that the silver chloride is less soluble than the silver chromate. Or we say that the silver chromate is more soluble than the silver chloride, either this or that. That's why the silver chloride precipitated first. Okay. Okay, Abdurrahman, some data obtained in the experiment are shown. Complete the table and use the concordant results to calculate the mean titer.
So the second titer would be 32.05 minus 16.15, which is 15.9.
15.9. Okay.
And the third one is 15.8. And number 4 is 15.85.
Okay, so what are the concordant titers here?
2 and 3 and 4.
Yes, excellent. We can take them all because they are plus minus 0.2. And so the mean titer will be
15.9. plus
15.8.
15.8
Ah, okay.
plus 15.85.
Yes.
Which
15.85.
yes.
Okay. So determine the value of X in the formula of the hydrated salt barium chloride. I would like Alishba to start this, please, Alishba. Now we know that, thank you, Abdurrahman. So here we determine the volume of the titer, the mean volume. And now they want you to find the value of X in the formula of the hydrated salt. Of course, we are going to use all the information they gave us and show your working, and it has 5 marks. So what do we start with, the Alishba?
To find out the number of moles of barium chloride.
Okay, they are titrating with what, ya Alishba? Yani, what is this titer? Here they said what? What was the titration between what and what? It was between the silver and the chloride, isn't it? Would you please
Yes,
read? So what is this volume? This volume was for what? Would you please read?
1 second.
Yes, please.
A silver nitrate solution.
Yes, excellent. So what is the first step to get the number of moles of what?
Of the silver nitrate solution.
Yes, excellent. And
So
how can we get it? Yes.
the volume times the concentration.
Yes. So what am I going to write here?
15.85
Yes.
divided by 1,000
Excellent.
times by the concentration, which is 0.0324.
Excellent. What did you get?
Uh, 5.154 times 10 to the minus 4.
Okay, excellent.
Miss 5.1354.
5.1354. Okay. And then they want determine the value of X in the hydrated barium chloride. So what are we going to do next?
So would you have to see the equation and see the ratio?
Yes, excellent. So which equation shall you choose? Reaction 1 or reaction 2? What we want to determine?
The number of moles of water.
No, we don't calculate يعني never we calculate the number of moles of water. We calculate the number of the solutions that we are titrating each other with, isn't it? You found the number of moles of silver. So what do you get afterwards?
Sorry, Miss, can you go back to the question?
Yes.
So they want us to work out the number of moles of
Yes.
water in the BaCl that's been dissolved.
Yes, they want the X. Yes, they want the number of moles of the water. Yes, but of course we cannot get the number of moles of water from the titration. We do not titrate water against anything. Okay, what are you
Yes.
titrating here? If you look here at the equations, what are you titrating? You are titrating the silver ions with the chloride ions, isn't it?
Yes, miss.
And from where does this chloride ion come?
From the silver chloride.
No, when the silver ion reacts with the chloride ions, it forms silver chloride. But the silver ion reacts with the barium chloride, isn't it? We started with the barium chloride. Yes, we started with the
Yes.
barium chloride and we dissolved this barium chloride in water. We dissolved it in water and we took only part of this solution and titrated the barium chloride against the silver nitrate, isn't it? Of course, we got rid of the barium, but we titrated the chloride ions that resulted from the barium chloride with silver nitrate. So this is what we are dealing with, the silver ions and the chloride ions. Okay?
Okay.
Understand يا أليشبا ولا you don't understand?
Yes, I understand.
Type. Okay, so from the mole ratio here, the mole ratio is 1:1, which means that the number of moles of silver nitrate is the same as the number of moles of the chloride. It's the same. Okay, but we are not dealing with the chloride ion alone. Well, here the mole ratio is 1:1, but in barium chloride, each barium chloride would produce how many chloride ions? Produces 2 chloride ions, isn't it? Which means that in barium chloride, we have 2 moles of chloride, not only 1, which means that the number of moles of, when we say that barium chloride gives 2 chloride ions, so if you get the number of moles of chloride ions to be 5.1354 times 10 to the power minus 4, so what will be the number of moles of the barium chloride? Understand what I'm doing? And here from the mole ratio here between silver ion and chloride ion, as the mole ratio is 1:1, this means that the number of moles of the chloride is equal to this value, the same as that of the silver ions. But we don't want the chloride, we want the barium chloride. So we say that every mole of barium chloride 0.x water contains 2 moles of chloride. So if you have this number of moles of chloride, so what will be the number of moles of barium chloride? So we divide this by 2, isn't it?
Yes.
So
would you divide it by 2 and then add it to the 5.154?
No, you divide it by 2 only. You don't add anything. From the mole ratio here, you get the number of moles of the barium chloride 0.x water.
Oh,
you
okay.
understand? So we are
Yes.
going to divide this by 2. We get 2.06 and then what? 7 times 10 to the power minus 4 moles. Yes.
Okay, yes.
But as I told you yesterday and every day, that usually they prepare the solution in a certain volume and they take only part of it to make the titration. So this number of moles of barium chloride is present in the 10 centimeter cube that they titrated, isn't it?
Miss, I think it's 2.5677.
2.5. Okay. Type 2.5677 times 10 to the power minus 4 are present in the 10 centimeter cube that they titrated it. So what will be the number of moles in 250 centimeter cube, the volume that they prepared the solution in? Understand, Yarish, what I'm doing?
Yes.
So by cross multiplication, it will be, you are going to multiply 2.5677 times 10 to the power minus 4 times 250 divided by 10, as if you are going to multiply it by 25.
Yes. You get 6.41925 times 10 to the minus 3.
Okay. Understand till now, or do you have any point that you do not understand?
I understand this.
Type. But we don't want only the number of moles. They said we have to find out the X, which is the number of moles of water. So what are we going to do?
which
What are we going to do, Mavi, afterwards?
We're going to subtract the mass that we got from the total mass.
Okay, but we didn't get a mass. We just
No.
got the number of moles. So how can you get the mass?
times it by
we're
the
going-
MR.
Yes, excellent. We find the MR, isn't it? Yes, Mavi, or not?
Yeah, I want to say so.
Okay. So how, Mavi, are we going to get it?
We're going to then multiply the mass by the MR of the BaCl2.
So the MR equal
1 second, please.
the mass over the number of moles, isn't it?
Yes.
So what is the mass?
Isn't that the thing we're going to calculate?
No, they gave us the
Oh
mass
yeah,
of the
it's
whole compound.
1.57, I'm sorry.
Yes, excellent. 1.57 divided by,
The molar mass, which is 6.41925 times 10 to the power of -3.
yes, the number of moles. So what do we get?
We get 244.58.
Okay, these are the grams per mole. Now, how can we get by X?
You're then gonna now subtract the mass of the barium chloride, the
Excellent.
anhydrous.
Yes, excellent. So the barium is 137 plus 2 chloride 71. So we get 208. So we
And when you
subtract the
subtract, you get
208.
36.58.
Okay, so this is the mass of water. So what are we going to do to get X?
Divide by 18.
Yes, excellent. So 36.58 divided by 18, we get 2, which means that,
2.0.
yes, so we say that X equal 2.
Yes.
Yes, excellent, Iman. Excellent, Alish, and excellent, Mavi. You understand all what we are doing here in this problem? I know it's too long, but it has 5 marks, so we have to, we have to do it. We don't have to say no, we cannot solve it. It has 5 marks. When you start, you will see that every step brings the other. Okay. Any question here? Type. Okay. Type. Okay. Whose turn? Miral. Number 4. This question is about the preparation of anhydrous aluminum chloride, which reacts vigorously with water. The aluminum chloride reacts vigorously with water and must be stored in tightly sealed containers. A sample of anhydrous aluminum chloride was prepared by passing chlorine gas over hot aluminum foil. Passing chlorine gas over hot aluminum foil using the apparatus shown. Here they put concentrated hydrochloric acid. Here is the potassium manganate 7. And then ceramic wool plug, anhydrous calcium chloride, aluminum foil. The aluminum reacts with chlorine gas to form aluminum chloride solid. And then here we have an absorption tube. Here we have a ceramic wool plugs, and here potassium hydroxide, and here a receiver bottle. Okay, would you all please read the steps? Okay, did you read the experiment?
Yes, doctor.
Okay. Granules of anhydrous calcium chloride are held between two ceramic wool plugs in the combustion tube. Explain the purpose of the anhydrous calcium chloride.
It's a drying agent, so it removes the
Yes.
water, so it
Yes,
doesn't.
yes, excellent. As Miral said, as calcium chloride is a drying agent, so it can remove the water from the chlorine. It absorbs water from the chlorine because here we want chlorine to pass through the aluminum foil. And they said that in order for chlorine to be produced, we are going to add concentrated hydrochloric acid to the potassium manganate 7. So chlorine gas is going to be obtained. And they place here the calcium chloride, the anhydrous calcium chloride, as it's going to dry or to remove the water from the chlorine gas. We don't want water to pass through the aluminum foil. We want only chlorine to pass so as to form the aluminum chloride. Otherwise, of course, the water that is present would react with the aluminum chloride, because of course we know that aluminum does not react with water, but if aluminum chloride starts to form, it can react with the water. Yes, excellent, Miral. So Miral, give the reason why granules of anhydrous calcium chloride are used rather than powder.
The calcium chloride isn't going to react with the chlorine gas, so it won't use it up before it reacts with the aluminum.
Okay, they say here, give a reason why granules of anhydrous calcium chloride are used rather than the powder. We know that the granules have spaces between them, isn't it? If you have granules, there are spaces. So the chlorine gas can pass through the spaces. But if you have a powder, there are no spaces to allow the chlorine to pass through. The spaces are very, very small. So the chlorine gas will not pass through the powder except with difficulty. Okay, so here when they said, give a reason why granules of anhydrous calcium chloride are used rather than powder, that's because to allow the chlorine gas to pass through the granules. If it's a powder, it will not be allowed to pass through it. How it will pass, but with difficulty. Okay.
Okay, Miss, thank you.
You're welcome. Rodina, the reaction occurring in step 2 produces chlorine gas. Carefully open the tap of the funnel, allowing the acid to enter the pear-shaped flask drop by drop to form the chlorine. Okay, so the reaction occurring in step 2 produces chlorine gas. Identify the main hazard related to chlorine gas, giving the best way of minimizing the risk when using this gas. What is the main hazard of using chlorine?
Chlorine is a poisonous gas, and
Excellent.
to minimize the risk, you can carry out the experiment in a fume cupboard.
Bravo, Aliki. Excellent. Chlorine is a toxic gas, and in order to work with it, we have to work in a fuming cupboard. Excellent. Give a reason, Rodina, why concentrated hydrochloric acid is added drop by drop to the pear-shaped flask.
So that the rate of reaction is not too high to control it.
Okay. So that the rate of the reaction becomes slower, you mean?
Yeah, so that it's not too vigorous.
Yes, excellent. To prevent the reaction to be, I told you before not to say vigorous, yani, just say to decrease the rate of the reaction. You can say so. Okay, so it is added drop by drop so as to decrease the rate of the reaction as the reaction. Yes, you mean yani, the reaction itself is vigorous?
Yes, if you do it too.
Okay. Yes, if you add yani, more than drop by drop, then the reaction would be vigorous. Okay. So you have to say to decrease the rate of the reaction. Yes, that's all. Type suggest, Abdurrahman suggest, excellent, Yerodaya, suggest why the heating of aluminum in step 3 is displayed by 20 minutes after the initial production of chlorine gas.
Can I see step 3?
In step 2, they said wait for 20 seconds. After they added the HCl to the potassium manganate, they waited for 20 seconds before they started to heat the aluminum foil.
To allow the chlorine to reach the aluminum foil?
Yes, excellent. Because here there was air at the beginning. So if they started to heat the aluminum foil at the beginning, then the aluminum would react with the oxygen that is present in the air. So they don't want that. They want the aluminum only to react with the chlorine. So to give time for the chlorine to fill this part of the tube and start to react with the aluminum. Okay, so allow the chlorine to take place of the oxygen and or the air and react with the aluminum foil. Mavi? No, I am the one to be sorry, but I wanted to finish this paper, but maybe we will not be able to finish it. So okay, يعني okay, you have to complete the test by yourself. Okay. But خلاص يعني we have to finish it. Yes, Yerodai. So if you want to يعني leave your Mavi, if you have anything else, please do. Type, okay. So there's only 2 points left. So here suggests why the heating of aluminum in step 3 is delayed by 20 seconds after the initial production of the chlorine gas, as Abdurrahman said, to allow for the chlorine to take the place of the air in order to react with the aluminum. Okay, Abdurrahman, state how you would know the reaction is complete in step 3. How would you know that the reaction has finished in step 3?
There's solids forming in the receiver flask.
Yes, there is a solid that is formed, which is the aluminum chloride. But how can we know that all the aluminum is formed now aluminum chloride? No aluminum is present. Okay. Yes, excellent, Yamavi, because they said here that heat the aluminum foil until it glows brightly. So if all the aluminum foil stops glowing brightly, this means that the aluminum now is finished. All of it reacted with the chlorine and formed the aluminum chloride. Okay. So how can we know that the reaction stopped? When the aluminum foil stops glowing brightly. This means that all of it reacted to form the aluminum chloride solid. Suggest the purpose of the potassium hydroxide in the absorption tube. Yes, Yamavi. To finish, but why do we
Can
add
you
sodium
please go up?
hydroxide? Yes,
Can you please go to the diagram?
yes. Now they said suggest the purpose of potassium hydroxide in the absorption tube. Yes, Yerodina,
I'm not
excellent.
sure.
Okay, now you are passing chlorine, isn't it? So
Yeah.
part of the chlorine will react with the aluminum foil to produce the aluminum chloride, and the excess of chlorine can be absorbed by the sodium or the potassium
Oh,
hydroxide
to prevent
because
it from escaping into the atmosphere?
yes, excellent. Because the chlorine is acidic and the sodium hydroxide or the potassium hydroxide is basic, so it will absorb it.
Oh,
Yes,
okay,
excellent.
yes, thank you.
You're welcome. Okay, thank you so much all, and I hope of course you do يعني try to solve as much as possible from past papers. I know that you have exams. I know that you have, I cannot give you another lesson tomorrow because you have bio in Wednesday. So when is your exam? Is it on Thursday or what?
Friday.
Friday. طب okay يعني then we can يعني I'm going to see if we can take a Wednesday lesson also. يعني if you'd like to have more lessons I can take you on Wednesday inshallah from 8 to 10 p.m. if you'd like to يعني I'm going to يعني to talk to you but after you finish your bio exam inshallah. Okay, inshallah, best of luck in all of your exams, not only chemistry, all of your exams. Thank you so much. I'm so sorry that I delayed your bedtime. So thank you so much. Bye bye.
No problem, doctor. Thank you so
You're
much.
welcome, dear.
Thank
Bye
you,
bye.
Miss. Bye.
You're welcome. Bye.